now we have discussed about the effect of growth of boundary layer over a immersed body, and we have concluded that depending on the shape of the body, the pressure gradient has a strong role to play. So, if the body has a particular curvature or maybe a bluff shape, then the pressure distribution on the body may give rise to interesting and important drag forces. Now, regarding the pressure distribution, it has to be remembered that there is a distinctive behavior if the boundary layer separation has occurred, but before the boundary layer separation has occurred, the pressure distribution is something which should follow as a consequence of what happens in the outer stream or the free stream, because one of the important assumptions or one of the important conclusions that we got from the boundary layer theory is that the pressure gradient which acts on the boundary layer is same as the pressure gradient what is imposed on it by the free stream. And if the pressure gradient has a strong role to play in terms of dictating the drag force, we have to quantitatively understand that how the pressure gradient acts on the body of a given shape, and for that a clue may be that what is the pressure gradient imposed on the body from the outer stream or outside the boundary layer. This is valid so long as the boundary layer theory itself is valid, that means so long as there is no boundary layer separation, but till there is boundary layer separation, till that limit one may use the boundary layer theory, and provided other assumptions are valid, that is Reynolds number is large, and then we may evaluate the effect of the pressure gradient without referring to the boundary layer, but just by referring to the free stream or far stream outside the boundary layer. And outside the boundary layer the flow does not understand the effect of viscosity. So, what is the typical characteristic of the flow outside the boundary layer? So, if you have a boundary layer like this, outside the boundary layer you have some free stream. The free stream velocity is u infinity, but as it goes past the body this may change because of the curvature of the body, and whatever is the important thing, what we have to keep in mind that initially, say if it was u infinity, that means if you consider say a 2-dimensional flow, for example, you have the x component of velocity as u infinity and y component of velocity as 0. Now, originally is it an irrotational flow? This is an irrotational flow. Now, an irrotational flow will remain irrotational if it is inviscid. So, outside the boundary layer the viscous effects are not felt, and therefore whatever flow was originally irrotational will tend to remain as irrotational, and when it remains irrotational always, we may always describe it through the gradient of a scalar potential. The velocity field we may always express through the gradient of a scalar potential if the velocity field is irrotational, and such a flow is known as potential flow. So, potential flow is therefore as good as inviscid and irrotational flow. The key here is that if it is irrotational initially as the free stream condition, but there are viscous effects inside, the viscous effects will make the irrotational flow a rotational one. Therefore, you must have an inviscid condition on the top of this one to make sure that it is irrotational forever for all conditions, so that for all conditions you may find out that for all conditions you have the velocity as the gradient of a scalar potential. It is important to look into the potential flow. See, when we discuss about potential flow, the first bottleneck or the first mental block that comes to our mind is that therefore we are talking about a case when viscous effects are not present, and when viscous effects are not present it is an ideal fluid flow. Will such a flow exist? The question is not whether viscosity is 0 or not, the question is whether effects of viscosity are important or not. So we have seen that outside the boundary layer the effect of viscosity is not directly important. It does not mean that the fluid has no viscosity, it simply means that the viscosity is not coming into the picture in terms of dictating the fluid dynamic characteristics, and therefore it is as good as inviscid flow outside the boundary layer. So when it is as good as inviscid flow outside the boundary layer, it is also irrotational as the free stream condition, it will remain as irrotational for the entire region over the body till you come to a condition where these conclusions you may never draw. The conclusion, thus what are those conditions? Boundary layer separation, because if boundary layer separation has occurred, there is no question of a boundary layer, no question of something outside the boundary layer, so all those things become irrelevant. So these considerations we may apply till the boundary layer is growing, till there is no boundary layer separation, but there is always a limit up to which the boundary layer is growing. At least up to that limit, if we want to evaluate what is the effect of the pressure gradient, it is important that we calculate the pressure field outside the boundary layer, because the same pressure field is imposed on the fluid in the boundary layer, and the pressure field outside the boundary layer may under these conditions be calculated by the potential flow theory, and that is why the potential flow is important even in the context when you have the effect of viscosity or boundary layer. The next question is that how should we approach for evaluating the velocity and the pressure fields in such a flow field. See, the potential flow cases, that is where you neglect the viscous effects, are really mathematicians' paradise, and that is how the entire subject of fluid mechanics initially developed through the mathematicians. And one of the important techniques by which this entire mathematical development occurred for potential flows, one of the important mathematical techniques was by using the theory of complex variables. So we will be using the theory of complex variables. Very briefly we will discuss that why theory of complex variables may be important in such a context, and how it may be utilized in this context, but we will mainly look into the developments using that theory, that how you generate different types of flow, different types of potential flows by using the calculus of complex variables. So we start with defining a function, say capital F, which is equal to phi plus I psi, where what is phi and what is psi? Phi is the velocity potential and psi is the stream function. So what kind of flow we are talking about? We are talking about case where both phi and psi are defined. So two dimensional incompressible irrotational flow, okay. So that is the example that we are taking. Now when you have this as f, see why we have chosen such an f. See, when you choose a complex number, say z equal to x plus iy, fundamentally it is ordered pair of real numbers x and y. These ordered pairs are chosen by some orthogonal basis x and y, okay. Here phi and psi are also two orthogonal bases, because we have seen lines of constant potential and the streamlines, that is lines of constant psi, are orthogonal to each other everywhere in the flow field except the stagnation point, right. Therefore this is sort of a mapping from, say, a complex plane with x and y as coordinates to phi and psi as coordinates, nothing more than that, but the orthogonality is preserved. So because they are orthogonal, we can choose such a complex function even preserving the general characteristics of what we have for such a complex number. Now the next thing is, what is the important advantage of this? See, if we write, so this is therefore a function of z, it is a sort of a transformation on z. So if we have such a function, what is the advantage that we extract out of it? The advantage is that in straight away in one shot we are writing the velocity, potential and stream function together through a single complex function. So if we write the complex function, then we may find its real and imaginary parts, one will give the stream function, other will give the velocity potential. So that is one of the straight mathematical advantages. Next, let us look into the differentiability of this function. We should remember that z is x plus iy. So let us try to find out what is df dz. The first question that we will like to answer is, does df dz exist or not? So to test that, we will soon see a criteria that what should be the corresponding test, but just let us try to look into it in a simple way. Okay. Now the simple reason is z is a function of x and y, right. So what is this one? This is 1, right, because z is x plus iy, and what is this? 1 by I, right. That means you multiply both numerator and denominator by I, so this becomes minus I. Okay. So now next step is, let us partially differentiate this with respect to x. So you have okay. So now what is the big test of the existence of these df dz for a complex function? One of the important tests is that the evaluation of the derivative should not be dependent on the direction in which it is calculated. See, now the direction is important because you are approaching, say you may approach a limit as delta z tends to 0 by using the definition of the limit, that delta z tends to 0 you may approach from various directions, because now it is not a single direction, it is a plane of points. So from, for example, you may choose to approach the limit as z tends to 0 by going in this way, you may choose by going in this way, you may choose by going in this way. So you may choose various directions in which you may approach towards the limit as z tends to 0. Now the existence of this derivative requires that the value of this df dz should not be dependent on the direction in which you approach in the limit to calculate the derivative. So that means that if you approach it along, say, x equal to constant line, that is along y axis, so what you get? If you approach it along y equal to constant, these are special directions, and if we satisfy these directions, any combination of these directions will satisfy, because these are two mutually orthogonal coordinate directions. Interestingly, you see that if you recall our basic fluid kinematics discussions, this is what? This is u, right, this is also u. What is this? V, and what is this? Minus V. So that means because we have u is equal to and V is equal to this one, you are having that no matter in whatever direction you calculate this, it comes out to be u minus IV, right, and that means this df dz exists because we may calculate it to be the same irrespective of the direction in which you are calculating. The whole key is because these conditions are satisfied. So not in general, but only for such cases when these relationships do exist. These are known as Cauchy-Riemann conditions. So when these Cauchy-Riemann conditions are satisfied, we can see that this df dz it exists, that means it is called as complex differentiable, that is it is differentiable in a complex sense. So that means it is complex differentiable, and such a function which is complex differentiable is also known as an analytic function in complex theory. That means f is analytic. That is, these are just terminologies, it is important to know these terminologies. So you see that if f is analytic, and yes, from our basic fluid mechanics considerations we show that yes it is analytic if we frame f in this way, then you see the next advantage is if you differentiate f with respect to z, this is once you know that it is differentiable, you write f as a function of z, its differentiation is just ordinary differentiation. So you write f as a function of z, find out df dz exactly in the same way as you could find out dy dx when y is a function of x. Then in one step you get another complex number, if you equate its real and imaginary parts you get u and v, the velocity components. So the strength of using this approach is if you frame a complex function, then its derivative where it's phi plus I psi, then its derivative directly will give you u minus iv, the velocity components u and v. Therefore it is a very convenient way of extracting the velocity components. Now this u minus iv is in the context of description through the Cartesian coordinate systems, but we may describe the same thing in terms of polar coordinate system. So let us try to see that how we describe it equivalently in terms of a polar coordinate system. So let us say that you have these as xy coordinates, and let us say that you have these as r theta coordinates. Along the r and theta directions you have the velocity components as say Vr and V theta. Along the xy components you have the velocity as u and v. Our objective is to write Vr and V theta in terms of u and v. So what is Vr? Or if we write u in terms of Vr, so u equal to Vr cos theta minus V theta sin theta. What is V? Vr sin theta plus V theta cos theta, right. So our complex function df dz was u minus iv. So let us just write u minus iv. So Vr cos theta minus V theta sin theta minus Vr I sin theta minus V theta I cos theta. So this you can write Vr minus I V theta into cos theta minus I sin theta. right. That means by using the de Moivre's theorem you can write this as Vr minus I V theta into e to the power of minus I theta. So we would remember that the alternative way of writing this in terms of the polar coordinates is u minus I V is as good as Vr minus I V theta into e to the power minus I theta, okay. Now the next thing is that with this mathematical background how we may utilize these to generate different flows. To understand that we will go through some examples.